Okay, so as I mentioned, in that case, we call that the forces vortex, 强制涡流. So that indicates we have another vortex. We call that the free. We call that the free vortex. Okay, so in the following slide, I will introduce how difference between the free and the forces. And then and I would like to emphasize again. So you have the z, the delta z in here is equal to the omega square divided 2g and the r square, right? So that's why the shape for the water surface will to be the parabolic, because the constant, there are the constant values to control the shape of the parabolic. Okay, so that you can try to image that if the omega is too large. So that means that if the omega increase a lot, and then the shape in here will to be much deeper, right? Because the omega increase. Okay, so that's you can adjust the different omega rotational speed, and then you can see the different surface profile shape. Okay, so that's the next semester we have the one experiment laboratory. We call that the vortex testing. So we have the vortex testings. Okay, and this is the device you will see in the next semester. And then you can see there are many pins. You can see that there are many pins. So the different pin, we trying to measure the surface profile, because you can put the water inside the pipe tank, right? And there are some the machine can control the different rotated angular speed, and you can see the surface profile will change with the different omega rotational speed. Okay, so in that case, we call that the first vortex. Okay, so what are the free vortex? So and the upper, we call that the forces test, the velocity is equal to the r multiplied the omega speed, angular speed. But for the free, the bottom one is we say that the free vortex, and the velocity is equal to proportional to the r over 1. So that difference velocity definitions, if the upper one is the forces vortex, and the bottom is the free. And then you see the free vortex, the surface profile to be a different shape. Okay, so how different? So I play the movies, and you can understand how the significant difference between two testings. So this is we call that the forces testing. And as you see the video, the machine is quite the new compared to ours. Okay, but the idea is totally the same. So you just make the table horizontal, and double check all of the machine. The node is fixed, and then you can have the pin and adjust. You can adjust the different omegas angular speed. Okay, and you can see the different omega speed for the water surface will change for a different shape. And we can know that the large angular speed will have the more deeper shape of the surface profile. And then you have the pin, and then you can measure the different elevations at the different locations. Okay, so in our laboratory experiment, you also have many pins, and you adjust the different angular speed and to observe the surface profile in your case. Okay, so this is the forced forecast experiment. So how about the free? So the free is the idea. Just put the water inside the tank, and you can see there is the hole. We have the hole. We open the hole, and the water will free flow, go through the hole, right? And you can see there are some forecasts. Okay. So the idea is quite simple. The force it indicates you apply the rotated speed in your machine. But for the free, we didn't apply anything. We just open the hole and the water will flow outside. OK， 好，那这个就很重要，所以一个是强制，一个是自由的。那我们刚才的 slide 已经写得很清楚了，自由涡流就是一个非旋流。然后强制涡流它是一个 rotational flow 这样子。哦，那这里给大家一个印象，就是说，不是说流体旋转就不可能是非旋流。你看刚才那个涡流不是也在转吗？可是它是非旋流。哦，所以只要你的流场满足我们说那个 theta rate 等于0，那个 vorticity 等于0，那其实就算你在旋转，你也是一个非旋流这样子。哦，满足那个公式，那其实就是非旋流的定义，不是说它旋转就一定是旋转流。哦，所以给大家一个印象，所以我们做实验的时候就会知道。OK， 所以我给大家一个举例，就是说你做摩天轮的时候，摩天轮不是也在旋转吗？可是你的脸是永远都朝着前面。你有看过你坐摩天轮，然后你跟着那个摩天轮的房子跟着一起转吗？不会，那种就叫做非旋流。就是整个东西在转，可是你的脸永远都是朝着正面的。那如果你做的是什么，有些东西，比如说做那个飞椅，假设是一个旋转咖啡杯好了，东西是在旋转，那你的脸不是从头到尾都在转方向吗？那这个就叫做旋转流。所以我们就是流体里面的一个水滴。当我们这个水滴有转的话，那就真的是一个旋转流这样子。哦，所以大家可以想象一下，坐摩天轮，你的脸不会转来转去，那个就叫做非旋流。Okay, so that's the very important comparison between the forces forecast and the free forecast. There are only two difference. The first one is the velocity formula are different. The forces forecast the velocity proportional to the r, but the velocity in free forecast is proportional to the r over 1, so the difference. And the forces forecast is the rotational flow, but the free forecast is irrotational flow. Okay, so that's the two difference, and when you conduct the laboratory experiment, you will fully understand how different they are. So in our class, I just introduced the principle between two different forecasts. But in the laboratory experiment, you can understand the reason why they are different. Okay, so that's for our testing. You need to illustrate the surface profile for the different forecast testings. So you need to plot some figures in our laboratory experiment. Okay, so and then this is a very good exercise also. So we have the U2, and you see this is 1.1, and there is the 0.2. And what's the problem? The problem is what are the new levels of the water in the tube after you apply the rotational angular speed. Okay, so in that case, we need to apply the Bernoulli equation for the rotational flow. Okay, so again, we just make the balance. So we have the P1 plus the gamma Z1, and minus, very important, we use the minus 2 over rho R1 square omega square will equal to the P2 plus the gamma Z2 and then the minus the 2 over rho R2 square omega square. Okay, so before we calculate the elevations, and we still reconsider how the condition we have. So we know that the P1 again will equal to the P2, and there is no gauge pressure. Okay, and the second, how the conditions we have the R1. R1 is the distance in here. So we know that the R1 is equal to 0.18 meters. And how about the R2? R2 is the length in here. So it's 0.36 meters. Okay, so we only have the two conditions. And the third condition is we know that the angular speed omega is equal to 8 radians per second. Okay, so we can put all of the information we know into the formula. So we just remove the P1 and the P2. Okay, and we reorganize the equations to be the gamma Z2 minus Z1, and the right hand side is 2 over rho omega square. Okay, and the R2 square minus the R1 square. Okay, and then we move the gamma to the right hand side. So we know that Z2 minus Z1 is equal to the 2g gravity over omega square, and the R2 square minus the R1 square. Okay, so in here we can put all of the number we already know. The omega is the 8, so the 8 square, and the 2 times gravity 9.81, and the multiply the R2 is 0.36 square minus the R1 is 0.18 square. So we can calculate the answer D2 minus D1 will equal to how many number we have. So use your calculator to check the number. Divided 2 divided 9.81. So for my calculators, the number showing calculator is 0.317. And in that case, we know that the unit is meter. But what's the problem? The problem is how large in the Z1 and the Z2. Because they just require we answer the new levels for the water. So, but we only have the one equations. We cannot answer the two unknown variable. So we need additional equations. So what are additional equations? Because we know that the conservation, because we assume the fluid didn't flow out. So that means the total height will the same. So we know that another equation, the Z1 plus the Z2, will always satisfy we have the 18 plus 18, right? Because the height in here will keep the same. Some of the two tube the height will keep the same, right? If the liquid didn't flow out. So we know that another equation will equal to the 36 centimeters will equal to 0.36 meter. Okay, so this is our equation 2. So we have the two equations, and we can find out the answer individually for Z1 and the Z2. So maybe the first we just 1 plus 2, and then we know that the 2 times Z2 will equal to the 0.317 plus the 0.36. Okay, and then you know that D2, how large it is. So you can use the calculator to double check the number is equal to the 0.338 meters. And you just put this number to maybe go back to the equation 1. And you can solve the Z1 is equal to 0.022 meters. Okay, so this is our final answers for our questions. Okay, so the idea is we apply the Bernoulli equation, but for the rotating flow, but the answer we need to the answer we need to are required for the new levels. So sometimes we need 2 equations to find out the 2 unknown variables. OK， 所以这个很常见，就是说通常我们不会只问你一个问题，这个问题是要你求新的抬升高度是多少，这个时候你通常都需要2个方程式。哦，那这个很重要，这个很重要。Okay, so this is almost our final exercise related to the rotation flow. So the ongoing the slide we would like to introduce the very important coefficients. We call that the pressure coefficients. And why we would like to introduce this coefficient, because you can see the items on the top. On the top is the piezometric pressure difference, right? So we have the piezometric pressure difference. And what the bottom? The bottom is the velocity. So we have the pressure. You can call that the velocity pressures. Okay? So in the upper and the bottom are related to the components for the Bernoulli equations. Okay, so if you compute the ratio between the piezometric pressure difference with the velocity pressure, and we call that the coefficient is CP, is the pressure coefficients. And this coefficient usually to be used to discuss with the drag force. What is the drag force? The drag force is one of the force acting on the particle surface. And we can separate 2 forces related to the drag. The first one is the pressure drag, and the second one is the frictional drag. And the frictional drag usually related to the viscosity effect. Okay, it's related to the viscosity effect. So we have the certain definitions. We call that the first one is the favorable pressure gradient, and another is the adverse pressure gradient. And how different for the condition? The favorable pressure gradient that indicates the flow condition is acceleration larger than 0. That means it's the acceleration conditions. But in contrast to the favorables, adverse, the acceleration is decelerations. So that's a difference. And the pressure gradient is smaller than 0, but the pressure gradient in here along the straight line is larger than 0. So what are the meanings? So I put the figures in here. So the circle in here, we call that is our body. Okay, it's our body. And we have some flow on the left hand side, flow to the right. Okay, and the particle would like to move to the left. The particle in here would like to move to the left. Okay, so how about the drag force? The drag force, it indicates resistance force. So the drag force with the directions opposite to the particle moving directions. OK， 那我们说的 drag force 其实就是一种阻力，阻力的意思就是说我想往前，可是阻力的方向是跟我前进的方向相反，那才叫阻力嘛。如果阻力的方向跟我前进方向一样，那不叫做顺推的力气嘛。OK， so usually the drag force is the direction is opposite to the object moving directions. And as I mentioned, in here, at this point, is a stagnation point. So there is no velocity at this point. So the pressure is the largest. And at this point, there is no lower pressure. So we have a larger velocity, flow velocity in here. So where is the favorable? In that stations along the x directions, the yellow line showing here, we call that the favorable. Okay, great, favorable pressure, and the right hand side, the curvature in here, we call that the diverse, or adverse. We call that the adverse regions. So what is the difference? Because there is the higher pressures, highest the pressures, and going here, there is a lower pressure. So, and the velocity in here is 0, but in here the velocity is the maximum. So we call that the favorable regions, we call that the accelerations. The flow condition is the acceleration. And the right hand side is the decelerations. OK， 所以在这里的话，我们可以看到这个前段是加速段，所以我们叫做 favorable 的这个 pressure gradient。那后段这边是减速段，所以我们说这是 adverse 的 pressure gradient。那为什么 That's the reason why the pressure at the pressure gradient is dP dx is smaller than 0. Because usually we have the higher pressures will flow to a lower pressure. So the gradient will smaller than 0. Right? Because the right hand is high and the left hand is high and the right hand is low. So the pressure to the right is decreased. So that the gradient is smaller than 0. But the right hand side, there is a lower pressure, but in here is a higher pressure. So that case, the dP along the dx will larger than 0. So in that case, the to the right hand side is a deceleration condition. It's a deceleration conditions. Okay, so I use the cartoon figure to see the different conditions. So the first one, you can see if the pressure gradient is smaller than 0, that indicates at this point the fluid particle is accelerating. So you see the du dy is larger than 0. That indicates the gradient in here is large. And then in that case, the gentle gradient for the velocity du dy, and in here the gradient is 0 equal to 0, but in here the gradient is smaller than 0. So that means there are some reverse flow because the flow velocity to be the negative in that area. So that's the ideas. You call that. We can see in that case, we put the velocity gradient located at a different location. And in here, you can see the adverse flow. So that means in that point, after this point, the flow will to be separate. Before this point, the flow will attach along the particle. And after this red point, the flow will separate. So that we call that this is the separated flow. And in that area, in our previous chapter, we call that there are some wake flow, right? 尾流. There are some wake flow in that area, and the wake flow is the lower pressure area. And there is a lower pressure area, and the environment is the higher pressure area. So you have the additional force along these directions. We have the additional force along these directions. Okay, additional force along these directions. Okay, so you have some return force, and if you compare the pressure in here, there is also higher pressure relative to the wake flow. So you have additional force along these directions. So this is also another drag force for the particle. Another drag force for the particle. Okay, so what I would like to mention is because usually this is a separation point, and after this point there are some wake flow. There are some wake flow in here, 尾流, and the wake flow will cause the lower pressure in conditions, and the lower pressure condition in here and will cause the large drag force. Will cause the large drag force, and the drag force we don't want to have the drag force. So if you can reduce the phenomena for the wake flow will be better. Okay, so how can we reduce the wake flow? So as you can see, there are some ideas to reduce the wake flow. Okay, so I move to some idea. That's the ball. This is the ball, and the separation point at here. And you see, we change some. We make the hole at the ball surface, and the separation move to another point in here. So in that case, we can reduce the wake flow regions. If we reduce the wake flow regions, and then we can reduce the drag force. So the ball can be moved easy, like the 高尔夫球. So you can see the 高尔夫 ball, we have made the hole on the ball surface, so that the ball can fly away. But you just throw the basketball ball. They are the smooth surface, so you cannot throw very far away. Okay, so that's the idea. We need to reduce the separation point, and then we can reduce the wake flow. So in that case, how can we apply the pressure coefficients? So we go back to see the formula. So we have the formula, how difference. If we have the positive Cp, what are the conditions? That indicate the piezometric pressures were larger than the piezometric pressures at the free stream conditions. If you have the negative Cp, that indicates the piezometric pressure smaller than the piezometric pressure at the free stream. So where is the free stream? In that area is the free stream area. So you just compare the piezometric pressure with the Pz0 in here. So if your pressure is larger than Pz0, that's you will have the positive Cp. If your pressure is smaller than the Pz0, you have a negative Cp. So the right hand side is we just would like to discuss how the Cp values along the P point, B point, C point, and the D point. Okay, so you see the line in here is the Cp curvature, and the inners in here is the positive, and the outer is the negative. So that means the pressure in here is large, right? In here is large because the pressure coefficient in here is positive. And the pressure in here is smaller. So there the pressure coefficient is negative. And on the back, on the front in here also to be the positive. And in here go back to the minus. Okay, so in the normal condition, if there is no flow separations, and then both sides in front and in back are the positive CP. OK， 你看我们左边这张图是没有分离流的，就是没有尾流。So the point in here and the right hand side are also positive coefficients. But if you change the different, in that case we have the wake flow in that regions. So we will have a lower pressure because the wake flow in here, so that's a rare lower pressure regions. Because the pressure to be lower, so the CP values in here to be negative. So you compare, there are two differences. The positive in here, but if you have the wake flow, there is a negative. There is a negative. Okay, so but we don't want the wake flow because the wake flow will provide the drag force along these directions. So the large drag force, the ball cannot fly. Okay, so sometimes for engineering problem, we would like to reduce the wake flow. And how can we reduce the wake flow? So the idea is you need to delay the separation point. So if your separation point occur early, and you will have a large region for the wake flow. So you just would like to move the separation point to the delay to move to here, and the wake flow region can significantly reduce. Okay, so sometimes we would like to how can we reduce the wake flow? So we can use increase the viscosity. We make the hole and the viscosity will increase, but the pressure drag will decrease. OK， 所以其实也不是说我们减少这个 wake flow 就没有任何的牺牲。我们因为去高尔夫球的表面挖了这些洞，会产生粘滞效果。所以我们是用粘滞力去换减少那个尾流的产生，但我们会多出一些粘滞力。那粘滞力其实对于球的影响比较小，那它还是可以飞很远。因为我们降低了它的那个pressure 的 drag 压力所造成的阻力。OK， 但是我们会提升粘滞力所造成的阻力。可是提升一点点粘滞力造成的阻力，远不及于那个压力所造成的阻力，所以我们可以改善，让球飞得更远。Okay, so that's the idea for the reduce the wake flow. Okay, so this slide just as I mentioned, because we increase the gradients of the velocity, so there will have the turbulent flow. The turbulent flow will relate to some viscosity effect. Okay, so we will increase the viscosity effect, but we can significantly reduce the wake flow. Okay, so how can we apply the coefficient for the pressures? So that's the idea, because the same we have the house, and the flow will have these directions. So the CP value in here should be the positive, right? Because the CP in here is a higher pressures, and the flow will flow to lateral, so we can flow to the lateral regions, and the lateral region we can have some wake flow occur. So in that case, there are some wake flow in that lateral regions, and as we see, we know that the wake flow will have a lower pressure, right? So in that region, the wake flow region is a lower pressure, and the house is a higher pressure. So the house would like to flow to outside. So as you can see, the force have these directions, and the CP value in here is negative. Okay, and on the top, on the front in here also the wake flow region, so we have lower pressures. Okay, so I have the one very quick exercise. As I mentioned, if the typhoon period, so you have the higher speed is 40 meters per second, and in that case, we're trying to understand the house, the pressure distributions along the house. So we assume the CP is 1, that indicated here, and we would like to calculate the force per meter square. How large the force per meter square? So we know that the CP is 1. We have the CP is 1, right? So is the 1 will equal to what are the pressures? The pressure, the P0, the gauge pressure is always equal to 0, right? Because it's a gauge pressure from the free stream side. But I just write down maybe here is a delta P, piezometric pressure, and because it's under the air, so the air density in here almost the 1.2. So we have the 1.2 kilograms per meter cubic, and the velocity we have in the free stream is the 40. So we have 40 square meter square per second square, and divided the 2. The number divided the 2. So you can calculate how large delta P we have. How large delta P we have. So we just use my calculator to compute the answer and divide it 2. So the delta P is equal to 960, and maybe the unit is the Newton per meter square, right? So actually we can answer the questions. We have the 960 newtons per meter square, and we can divide the 960 by the gravity. So we can calculate. So the 960 divided the gravity will equal to the around the 98 kilogram, right? So that's why I write down the number in here. So in that case, we need to the house on the front. The pressure will equal to around the 100 kilograms force. Okay, so you design a house, and you need to overcome the maximum force we have in the futures. Okay, so that based on this idea, we can follow the some house wide code. You see, there are some the table. You can double check the different condition. You have the different CP values, and if you would like to build the house, so you need to satisfy the tables. If your house didn't satisfy the table, it's illegal structures. So you see the different conditions, you have different CP values. So you need to design the structure can overcome the largest drag force in different conditions. Okay, so how about, and sometimes the table also have the L and the B ratio. The L is the longitude length for the house, and the B is the width of the house. Okay, so it depends on your house shape. If your house shape different, you need to apply the different CP values for your house. Okay, 那这个 CP value 其实很重要，就是我们在建筑法已经都有一些规范，所以你在盖房子，你的房子是长的还是方的还是扁的，那你就会有不同的 CP 值需要去满足这样子。 啊，你不能设计一个，然后就台风来了，然后门就被吹走了这样子，就这个门就直接飞走了这样子。OK，so that's the final slide。哦，那今天后面这个其实是比较应用的，所以你在课本里面比较难找到。哦，所以我才把它补充在这里。那主要的概念就是说，一般来讲，我们其实一定会有阻力。那我们要怎么减缓阻力？减缓阻力就是让分离点，让这里的分离点尽量往后延伸。因为只要这个分离点往后延伸的话，我们在后面的尾流的区域就会变小，然后会有阻力的额外的阻力产生，就是这个尾流所造成的阻力。哦，这个 wake flow 所造成的阻力。所以我们只是在想办法降低后面的尾流的这个大小，这样子。好，这是概念。然后这个 CP 值就可以让我们来去设计怎么减缓这个尾流。哦，怎么减缓这个尾流？因为你可以看到不同的 CP 值，像这个 CP 值是负的，所以这里的尾流就很严重。所以我们就是想办法要去减少这个尾流的效应的话，其实这里的 CP 值就会变得更小。哦，负的更大啦，但是就可能变负的 0.8 或是负的 0.6， 就是不可以有太多的尾流在这里产生。Okay, so I just find out some interesting movies on the website. You can see the title is what kind of Newton's law we have. As you can see the box, 保丽龙, the box just drive out and go return back.And jack out and return back. So the idea is the regions on the car outside is lower pressures. And it's a wake flow, so the lower pressure. And on the environment is a higher pressure. So the higher pressure push the lower pressure, and then so the box go return back. But in car, the some motion will drop the box outside, and so you can see the movie just go outside and return back, and go outside and return back. 哦，这个概念其实就是因为我们伯努利告诉我们，这个车体的后面会有尾流的产生。那尾流不是我们刚刚就一直讲它是低压环境吗？那低压环境的话，可是相对于环境的压力是高压的。所以高压会把它再挤回去，再把低压环境的东西再挤回去，所以你看那个箱子就会再跳回去。那当然网络上酷手的留言就很多嘛，然后他说一开始说这是牛顿第几定律，然后开始就有临界的定律出来了。那我觉得像这种酷手的不都用周星驰的这个梗吗？我又跳进去了，我又跳出来了啊！所以就是这个50几个留言里面只有一个人说这个是伯努利定律，所以一般人都不会知道这个现象原来跟伯努利定律是有关系的，当然其他都是酷手搞笑的。OK， 好，那我们今天就到这。那我先把